In this video, we're going to investigate another work calculation problem. We're going to see a different way that the force times distance plays out in this application. The scenario is that we have an aquarium that's 2 meters long. So it's 2 meters in this direction, and 1 meter wide, and 1 meter deep. We're asked to find the minimum amount of work needed to pump half of the water out of the aquarium. So it starts full, and then what we're going to do is pump out half the water. So I'll just do a front profile here. And that's going to indicate our final state. Now let's go back to our idea about work equals force times distance. Where is the challenge here? Well, if we look at all the water here that we're going to remove, so let's take this part of it. That's what we're going to be taking out of the aquarium. From an energy perspective, why does it take energy to do this? Well, because we're lifting the water up to the edge of the aquarium. However, that lift height is not the same. If we imagine a little slice towards the top here, this might only have to go up, say, 1 centimeter, whereas the water that we take out towards the end of our project here is going to have to go up by 50 centimeters or half a meter. So the distance is not constant. Okay, well, fortunately we have a way to handle that. We're going to break this problem down into small pieces and ask ourselves, how can that break down the total amount of work into smaller pieces where the distance is constant? So we need small work calculations where the distance is approximately constant. Well, how can we do that? If we take a look at all the water that we're lifting, in fact, going back to this diagram, we can see it. All of the water in this little slab here is going to be lifted roughly the same amount. What would be a good name for that slab of water? Well, we're going vertically, so how about delta y? So our goal now is to compute not the work of lifting all this water at once, because that is the challenge because the distance we're lifting is not constant, but instead compute work required to lift a slab of water that is delta y thick. And why is that more helpful? Well, because if we imagine all the water in a slab like this, then it is all being lifted by the same amount. That's going to make the distance lifted constant. On each slab. And let's emphasize that that is the lift distance because that's where we're moving in this particular scenario. Well, to do this accurately, we have actually almost everything that we need. The only ingredient missing right now is really a definition of our variables. So it makes sense to call the slab delta y thick, but one of the challenges in these problems is that's straightforward. We know the total dimension here is 1 meter, but we really need to define where y is. We know this is a change in y, but what are we going to define as y equals 0? Where's our axis start? And there's two natural choices. We can start from the top and then have y increase as we go down, or we're going to go the other way and have y start at 0 at the bottom and increase as we go up. There's no right or wrong answer to that. It just affects how you build up the equations later on. It doesn't change the total work, but it changes how your equations look along the way. All right, so now we're going to consider all the water in a slab which is at height y. So we're going to be up here at some height y, and with a thickness of the slab of delta y. Then the work to lift the slab to the top of the aquarium is going to be force times distance. Well, the distance now is relatively straightforward. Let's take a look at our picture here. If this total height is 1 meter from the top down to the bottom, and we are at height y from the bottom, then the remaining height is going to be 1 minus y. So our distance becomes 1 minus y. Now our force is where things get interesting. Force, in this scenario, how much force are we exerting? Well, we're resisting gravity, and so our force is going to be broken up into two pieces, mass times acceleration. We're pushing against the force of gravity, which has an acceleration due to g, so we're going to put that in. But we're also going to break down our mass. How much water are we lifting here? Well, it is going to be made up of the volume times the density. Sorry, I like building this up as a tree diagram because it makes it clear which parts are coming from where. Our acceleration is just g because it's gravity that we're fighting. And now we have the lift height constant at 1 minus y. So the work to lift the slab to the top is force times distance. That's mass times acceleration times distance. Mass is volume times density. And density, we know volume of this slab is going to be the interesting part. Let's take a top view on that for a second. We were told that this was a 2 meter long by 1 meter wide. So it's a 2 by 1 by a little bit, we mean delta y thick on the third dimension. And so our volume is going to be 2 times 1 times delta y. Now the density, we seem to be using meters. Let's use meters, kilograms as our tools here. That'll give us newtons and joules. Our density is 1,000 because the density of water is 1,000 kilograms per cubic meter. Gravity, our classic 9.8, and our lift height 1 minus y. And now we see all the ingredients that we need for the work to lift one slab. We can group this differently. In fact, we will, just focusing on that delta y. That's the kind of thing that's going to appear in our integral later on as dy. Let's put it towards the end and just reconstitute everything else here. Put our constants first. It's nice to be able to see the roots of all of these. So 2, 9.8 times 1,000. We have a 1 minus y, and we have a delta y. That's the work required to lift one slab to the top. Our final step is to configure an integral that'll capture the work required to lift every single slab up to the top. So the total work required is going to be the sum of the work for all slabs. And that's going to be represented by an integral as we let our delta y get smaller and smaller. And it's going to be based on this amount for each individual slab. So 2, 9.8, 1,000, 2, 9.8, 1,000, and 1 minus y. And the delta y turns into a dy. And that's almost everything. The only thing remaining is the limits of integration. So here we have to go back to our picture and the scenario in particular that said we were defining our y equals 0 to be at the bottom. Our y equals 1 was at the top, but we were only lifting out the top half of the water. The water in the bottom just stayed where it was. And going back to our definition of the slabs, we were lifting a slab at height y. The first slab we were going to lift is going to be the slab halfway up the aquarium at y equals 1/2. Remembering again that all of our units here were in meters for lengths. And the very last slab we're going to lift is at y equals 1. And if you just freeze for a moment here, you can see some of the relationships coming out. Here we have all this work, and then we have the lift height showing here. If we take a look at the y equals 1/2 as our lower end, when we take that slab, we're going to lift it another ½ meter. 1 minus 1/2 is 1/2. Whereas the slab right near the top takes almost no energy at all to lift. Well, that's represented here with y equals 1, 1 minus 1 is 0. The infinitesimal slab right at the top basically falls out of the aquarium all on its own. And it takes just more and more work as we work our way down the aquarium. If it came to evaluating this, we would be able to do that very easily. This integral has mostly constants and then a 1 minus y. That's straightforward. Rather than go through the details of that, though, I'd rather emphasize an important distinction here, or an important relationship, that if we wanted to calculate the total work in a different way, not a fundamentally different way, but just one that acknowledges that we could have defined y equals 0 at the top here and going larger and larger down to y equals 1 at the bottom. We would have gone through all the same process. In fact, the force calculation, volume, density, gravity, all of that would have been identical to what we did before because we're looking at just slabs of water. The thing that would have changed is the distance that we're lifting. So if we imagine a slab at some height y, now y is actually equal to the lift height. Well, how does that work? Well, we would have the integral of the mass of our slabs to 9.8 times 1,000 for the density, and then we had a delta y, we'd still have a dy here. The difference would be the y here is the lift height. Now that seems at first glance to be very different from this, so how can they represent the same thing? How can they be equal to each other? They have to be, because physics in the same scenario. Well, the answer is our limits of integration also changed to reflect that new definition of y. Here, the first slab that we're going to take is the slab at y equals 0, and the last slab that we're going to take is at y equals 1/2. The net effect is, with the new limits of integration, and this 1 minus y versus these limits of integration in y, you're actually doing a substitution between these two integrals. It's a little tougher to see because we use the same variable twice, but replacing 1 minus y with y and doing the same thing to the limits of integration, we get just a new form of exactly the same integral, both of which end up giving us a number of joules for the work required. All right, a couple of quick notes about this analysis. What we did here is we found the minimum amount of energy. This is very much in the vein of physics energy calculations where we're ignoring the idea of actually moving water, requiring friction, requiring pumps and tubes and all these other extraneous losses of energy. But there's a reason for that. If we're trying to compare the most fundamental aspects of this lift operation, what should take the most work is the actual lifting itself. Every other contributor should be a relatively small fraction of that. It also gives us that lower bound, so we know if we're comparing two scenarios, what's the best possible scenario, the least possible energy for both of those scenarios, then we can compare apples to apples. If it felt weird to think of that as work, well, if it's easier for you, by all means think of this as energy instead. And in that same vein of energy, we imagine this happening slowly because you could be thinking of this as sort of a potential energy argument. Absolutely. We wouldn't want to add more energy with a pump in the sense of adding kinetic energy. This is a scenario where we imagine just lifting the water to the top and giving it just enough height above the edge so it falls over, or it could fall over. We're not pushing it out once it reaches that top of the aquarium. And again, this is all standard building block, standard assumptions for energy calculations in typical physics scenarios. Now, could we add a lot extra information? Could we do a much more detailed study? We absolutely could. We could be talking about particles and the kinetics of particles. In an upper year physics courses, you may do that. The point of these calculations, though, is more to get a broad strokes idea of the energy requirements for a scenario as a minimal construction, as a minimal idea of what's actually happening. All of the extra details that are available to us are interesting and fascinating, but in many scenarios, they won't matter. They'll be less significant than the main driving force. That's like finding the major component of a cost and then having 100 other smaller costs associated with it. You're going to get the most bang for your buck, the most understanding if you focus on the largest possible source of cost, or here, the largest possible requirement of energy. The purpose of this approach is, if we look at energy conservation, it really simplifies the problem. And it's up to our professional judgment whether it's simplified it too far for a particular application or not. In many cases, we can be very surprised to find that actually this simplification is all we really need to get the ballpark figures that are required for a problem.